Hi, my name is Ali Shirsavar from Biricha Digital. If you've been trying to calculate the size of the output capacitors of your power converter, you have probably noticed that there are several different ways of doing it with different equations, each giving a different answer. So in this video, we're going to bring some clarity to the situation and show exactly what equations you need to use depending on your application. Okay, so let us say that I've got a power supply, for simplicity, 5 volts and 2 amps. Now, in an ideal world, I would like this power supply to stay at 5 volts regardless of what load I have. So if I give it a load step, in an ideal world, I don't want it to dip. Also, in an ideal world, I would like there to be no ripple on this output voltage at all. And of course, in real life, it doesn't happen like that. There will be some ripple as a result of the switching action of the power supply. And of course, there will be a certain amount of dip when I give my power supply a load step. And the job of our output capacitor is twofold. It's to reduce the ripple and it is to minimize this amount of dip depending on our application. And that's why sometimes you get many different equations for each one of these. So I will talk about the ripple a little bit later on. Let us first work out what is the size of the capacitance that we need depending on the amount of dip that we can tolerate. So starting with my 5 volts, let us say that I give a 50% load step to this power supply. I said that my output current was 2 amps, so I'm stepping from 1 amps to 2 amps. That is a 50% load step, which is very common in the specifications that often we're given for power supplies. And therefore, the load step, my delta I, is going to be 1 amps. I'm going to need that in order to calculate the size of the capacitor that I need. Then, let us also say that when this 1 amp load step occurs, I do not wish this output to fall below a certain level until the control loop starts to react. Again, this dip, delta V, is often given, but if it's not, somewhere between 3 to 5% of V out is not a bad number. So my V out is 5 volts. 5% of that will give me 250 millivolts. So I've got a second number that I can use in order to size this output capacitor. I've got a current step of 1 amp and a voltage dip of 250 millivolts. The third number that I need is how much time I have before the control loop gets activated. And let's just call this T dip. So the amount of time that is going to fall down. The capacitor will have to hold this voltage above a 240 millivolt drop until the voltage loop, until the control loop starts to get activated. You can imagine that if you've got a really slow control loop, then this will take a long time to recover. And if you've got a really fast one, then it's got a little time. It will take a little time to recover. And of course, this will then determine the size of my capacitor based on the response time of my control loop, which is directly proportional to what we call the crossover frequency. Please don't worry, we have done other videos which talks about the crossover frequency and control loop design. If you're doing the online workshop, there is an entire section on how we design a good control loop. But for now, if crossover frequency is given, a good TP would be approximately 1 over 2 pi fx, where fx is your crossover frequency. If it's not given and you wish to still size your capacitor, then a good value for TP is around 3.2 to 5 switching cycles. Let us say that my switching frequency Fs was 200 kilohertz. Then 5 switching cycles would give me 5 times the period of this one switching cycle for a 200 kilohertz power supply would be 5 microseconds, which is 25 microseconds. So that is the third number that I need. My T dip here is 25 microseconds. And I can now, based on these three values, I can go and calculate the size of my capacitor literally from using a school level physics equation, which if you remember, we knew that Q was equal to CV, where Q is equal to IT. So IT is equal to CV. I know this, I know this, I know this, and I can calculate this. So I'm going to wipe the board, and then we're going to give you a numerical example. Okay, so far I know that my power supply has got a V out of 5 volts. It's got a current of 1 amps. We allowed a total dip voltage of 5% of that, which was 250 millivolts. And we said an step, the step was, I beg your pardon, this was 2 amps. A step of 1 amps. And then we said that our T dip was 5 switching cycles. The switching frequency was 200 kilohertz, which gave me 5 microseconds per switching cycle, and therefore the 5 switching cycles would be 25 microseconds. Then we know Q is equal to CV, and that gives me IT is equal to CV. I'm going to rearrange this and put the deltas on. So we know that C is equal to delta I T dip over delta V. So I have 1 amps times 25 microseconds divided by 250 millivolts, which gives me 100 microfarads. That's C out min. There we go. So this is the absolute minimum capacitance that we need so that we do not violate this requirement over here. I can have more than this, but for sure I cannot have less than this. So we're going to say C out min has to be bigger than 100 microfarad. Now, these were the requirements that I had for the dip voltage. But remember, we also need to minimize the ripple. So we're going to have to calculate it again, and then whichever value is bigger is the one that we're going to use. So now we're going to recalculate the value of our output capacitor based on the ripple requirement. This now depends on whether we are using predominantly ceramic capacitors or predominantly electrolytic capacitors. For low voltage, high current power supplies, like the ones feeding, let's say, FPGAs, point of load for big microprocessors and so on, usually the output capacitors are predominantly ceramic. So I'm going to talk about that one first, and then we'll talk about the electrolytics a little bit later. So let us say that I have a point of load buck and the output of this will have a certain amount of ripple, the out. And if this is predominantly ceramic, or let's say film, the ripple actually looks a little bit like this at the switching frequency. And I want to reduce this below a certain level that is specified in the data sheet. I beg your pardon, in the specification. So again, if I have for simplicity a 5-volt power supply, this is almost always specified. If not, 1% is not a bad value. So 1% of 5 volts would be this ripple. I'm going to call this delta V ripple now. Let me use a different color. Delta V ripple of 5 millivolts. So I need to attenuate the total ripple so that it's less than 5 millivolts. I know that the actual ripple current that is going through here, which looks like this. And I know this already because it's the peak-to-peak ripple current of the inductor, delta I ripple. And the inductor was one of the first things that we designed when we designed a power supply. Again, if you're watching on YouTube, there's plenty of material. We've done videos on this already. If you're taking the online workshop, the first thing that we did was calculate this delta I ripple. And let us say that is 800 milliamps, just for simplicity. Then for a buck converter, the equation is C out is equal to delta I ripple divided by 8 times the switching frequency, we had it at 200 kilohertz, times the total permissible ripple, which in my case delta V ripple. Yeah, so this was 800 milliamps. 8, I know switching frequency was 200 kilohertz. This is 5 millivolts. And you calculate, therefore, the new size of this value. And whichever value of these two is the bigger one is the amount of capacitance that you need for a power supply that has got ceramic capacitors on the output. Please remember that ceramic capacitors have got something called a DC bias loss. Their value really collapses as you increase the DC voltage on it. Allow yourself a factor 2. So if you're calculating 100 microfarad, add an extra 100 microfarad on top, and 200 microfarad is the amount of capacitance that you need. And there we go. We have calculated the size of capacitors that we need, provided that we have a point of load converter, in our case a buck, with ceramic capacitors. If you're using a different topology such as boost, flyback and so on, the procedure stays exactly the same. It's just that this equation here changes depending on the topology. And with 3 minutes on the internet, you'll find what the correct value for the correct equation is. And of course, if you're taking the online workshop, our power supply design software, Biricha WDS, has got all of these equations for most of the common topologies already built in. So the next thing that we're going to do is look at power supplies that have electrolytic capacitors instead of ceramic capacitors. Okay, so let us now look at a case whereby our power supply has got electrolytic capacitors on the output as opposed to predominantly ceramic. So we've got predominantly electrolytics, which is actually by far more common. Now the issue is that, let me draw another simple buck. Up until now, we assumed that this capacitor here is ideal. And that is not unreasonable if you're using ceramics, because the equivalent series resistance of this capacitor, the parasitic resistance of this capacitor, for ceramics is so low that we can actually ignore it. We cannot do that for electrolytics. So an electrolytic capacitor has got a significant amount of what we call equivalent series resistance, or ESR. And of course, the ripple that appears here is a function of this, that is V ripple due to the ESR, and then a function of that, V ripple due to the capacitance. Now, very similar to the ceramic capacitor example, whereby we ignored ESR because we said that it was negligible. Actually, the amount of ripple that is as a result of ESR for the electrolytic capacitor is by far greater than the amount of ripple that we get as a result of the capacitance at the switching frequency, which is where our ripple is. And therefore, we can really simplify things by actually ignoring this, and we say that the total ripple that we have is as a result of that. Again, I know the peak-to-peak ripple current. I know the so we said peak-to-peak I ripple. Following on from the previous example was 800 milliamps. Let's say that a specification for our ripple voltage, peak-to-peak voltage ripple. I noticed that I made a mistake. 1% of 5 volts is 50 millivolts and not 5 millivolts, but it doesn't matter. The principle stays the same. So let us correct that. 50 millivolts. And then we quite literally just use Ohm's law. V is equal to IR In my case, that is ESR. Okay, so I know 50 millivolts is equal to 800 milliamps times ESR. So I can work out ESR is 50 millivolts divided by 800 milliamps, which in this particular case gives me 63 milliohms. Now, the manufacturers provide the ESR for you, and provided that you find yourself a capacitor with a ESR of less than 63 milliohms, then you will not violate the ripple requirement. So all we have to do then, in this case, actually the size of capacitance doesn't matter. We go and find a capacitor with an ESR of 63 milliohms at the switching frequency, at Fs, regardless of its capacitance, provided that it's bigger than this value. So we need a minimum amount of capacitance that's going to be 100 microfarads and a maximum amount of ESR, which will be this. We can just go to our manufacturer's website and find the correct amount of capacitance, and then we are done. We have calculated the size of the capacitor with the correct amount of ESR. So that's it. I hope you enjoyed the video, and I hope to see you in one of our workshops.